whenever we are designing any architecture, there are the two different parts of this architecture. One is the software and second is the hardware. So now we are pre-assuming that we know the requirement, we know the specification, and we know the models also, and then we are trying to fix up the architecture. And when we are trying to fix up the architecture, so first part is the hardware part and second is the software. So within that software or within that hardware, then we know that how many parameters or how many functions that should be executed by that system, and then how that should be controlled. And when we know that how to be controlled, then we require the controller. So here we'll think how we can select that processor or that controller for the any embedded designing. So yesterday we went to the that ARM, how that ARM is suitable for the embedded designing, and for that one we have just taken up the different parameters. One is the low cost, second is the low power consumption. The third one is that is the size. Okay, the die size is very small, and as the die size is very small, then we can use that with the size of that arm is small. Again, the cost is very small. The cost is small means the cost is low. So today we'll move further for this embedded designing. Whenever there are the different parameters, then how we can select the CPU. So normally whenever we are selecting the CPU, we always say that it is a hardware issue, isn't it? But nowadays, the selection of that CPU, that is not only the hardware issues, but also the software. With respect to the software, okay, what type of the routines are there, what types of the algorithm that need to execute it. So depending upon that software issues also, we should check the CPUs. Hello. Yeah. So we can say not only the hardware engineers, they will select the CPU, as well as the software development team also check it out, what type of the CPU may needed along with that embedded designing. So here we are going with this different criteria. The first one is the hardware-based selection that depends upon the power consumed by that chip. The power is going to be delivered by that chip. Then the facilities that are available along with that CPU, okay, and then the last is the price and the available, it is available in market or not. So as a hardware engineer, we are just checking out only these parameters. One is the power consumption, then the deliver uh, with respect to that CPU. So power deliver with respect to that CPU means if the signal which has been provided by the CPU and that CPU signal is available along with only 1 volt, or suppose point or point of 5 volt or some 100 millivolt, and if this signal is going to be passed from that device to the any other device, then we need the intermediate amplification, so that amplified signal that should be reached to the different devices or to the other devices. So we have to consider such type of the parameters when we are selecting upon that CPU, and all this information is available into that the data sheet which is available along with that CPU. So we as an engineer will find out what type of the power would be there in that embedded designing, and depending upon that power requirement or consumption, will select what type of the CPU would be there for that embedded design. Then what are the facilities that are provided by that device? So the additional means, if that is a microcontroller, then how many IO are available? The timer, is it available or not? Counter is available or not? So what the facilities are there along with this that ARM processor, rather than only for the execution of any routines. Okay, so these are the hardware-based selection, but for the software also there are the many consideration are there, so that the software team, they will define which type of the CPU should be there. The first one is that whenever the software team would like to define which type of the CPU should be there for the designing, then they should be familiar along with the CPU architecture. Okay, so you just concentrate on this part. Okay, why the software team, they are concerned along with what type of the CPU should be there along with this embedded product. Okay, so for that one, so before that one, they should know the different types of the CPU architecture. Why that software engineer wants that CPU? Okay, so we'll go with the first one. Okay, so does the team have the development tool for the CPU? Okay, so there are the different tools. These are connected. These are required. Okay, for this team. Okay, for then that tools these are be available along with their CPU or not. So if that tools are not available, for example, the one example we can take. Suppose we are having the uh, uh, one software that is the IDE, or we can say the second one, the Nile software, okay, or the Arduino board, okay. So for that one, we require some development softwares on which we are designing the our whole design that embedded product, and then within that one we are just mentioning one CPU. So that development tool that should be analog along with the CPU or not. So that software engineer, the software team should know what type of the development tools are going to be used by that team that should be compatible along with the, what type of the CPU is going to be selected. Then second is the simulation models. Okay, so we are not directly going for the hardware. So we are first we are going for the simulation, and then after we are getting some result, then only we are going for the hardware. So this simulations software, for example, if you are going for the MATLAB, and within that one you are using the simulation modeling, and once you select that simulation modeling, and then that code which is available after simulation, so that may available into the M file, then you are converting that into the C or C++ or embedded C. Okay, then this whole executable file that should be download. You can download it to your system. So your CPU should be compatible along with this all executable file, where your CPU can interact or that can react or can act, and depending upon what executable file is going to be downloaded along with that CPU. Then what type of the operating systems are going to be supported along with your proposed CPU? So the Linux, and then the embedded, the RTOS or that Microsoft. So what you require, and depending upon that one, you are having that CPU. So whether you are the software team member, then we should know the different types of the CPU architectures, and then you can select the development tools. You can select the simulation modules in a such way that the available CPU which are available with you, depending upon that one, you are selecting these development tools or you are selecting the simulation model, so that you can match your all results and you can execute all your results on that hardware. Otherwise, then you have to demand it. Okay, as a software team, you have to demand it. Okay, we have done this part, and then we require such type of the CPU, and then only our algorithm get executed. Then next part is the low power modes. So the CPU, when we are having the CPU along with this embedded, or we can say that ARM. So we are having the variety of that ARM processor. So out of that one, which ARM processor that has to be used for this embedded product. So we have to check it out. The each and every algorithm that is needed there, or can you stop it, or can you just mute, you can keep that CPU in a sleep mode, and so that you can do something else function, so that the power consumption get reduced. So uh, so this power budget, okay, or the what here, that is a dynamic voltage and the frequency selection designing. In the designing, if you are select going with this way, then uh, you have to make that CPU that might be in the sleep mode, or that might into the with working condition, or that may be in wait condition. So depending upon what type of the operations are going to be executing outside of that CPU, because one processor, and then we are having the peripherals. So when the peripherals are executing, you are not doing anything for the CPU. So if you are not doing along with the CPU, then why you should provide the sufficient power for the CPU? You can only provide the power only for the initialization purpose, isn't it? So you can reduce the power to the CPU in a such a way that only some of the registers that can be initialized, the rest of parts might be in sleep mode. So that is fine. So this such type of the decision can be taken up uh, by this software development team. So whenever that development team, they are having the different routines, and depending upon that routines, they will check it out how many routines that should be executed at which time. And depending upon that one, then they require okay, my CPU should be work into the 3 or 4 different modes, so that the power consumption may get reduced. So there are yesterday we went through the different versions of that arm. Okay, so we are having the arm that is for the thumb with the T extension, that is with the thumb. Okay, then we are having the extension along with the S, that is a synthesizable. So uh, there are the second one is along with the J, that is along with the that date what we can say, that is a Java microbytes code can be executed along with this arm. So depending upon what type of the algorithm that you need. Okay, for example, you are having one algorithm where you are writing the code for the 16 bit, for the 32 bit, and then you are just switching off between this 32 bit and 16 bit. So 32 bit for your main program and 16 bit only for the sending the data to the IO devices, isn't it? And if you are doing that one, you are just sensing the data from that IO and getting the data from that IO, so that you can work within your whole program that might be 32 bit. And if you require this frequently, then you can choose the arm along with the T, that is along with the thumb, so that you are having that facility to run some program in 16 bit, and you can run some part into the 32 bit, so that the costing of that CPU and the right utilization of the CPU would be there along with the highest performance. Okay. Otherwise, if you are not using along with that T, then unnecessary that 16-bit data, it has to be extended with the 32-bit data, and then you have to do operation on that one. So unnecessary the additional operation get increased along with your routines. So this is what the part of that the team. Okay, that's system software, or that developer team. Okay, what type of the routines are there? What type of the functions are there? You know, and depending upon that one, then you can select what type of the CPU would be there. Then the most important part is just identify the domain of that applications. Okay, so there are the different types of the domain. One is the automotive, second is the industrial automation, then the medical electronics, defense, consumer electronics, mobile. Okay, and depending upon that one, there are the various requirements are there. Okay, so what is the requirement for the automotive, that is not there for the medical. Okay, so what the requirement is for the medical, that is not for the industrial automation. Okay, so depending upon this uh, different verticals or different application, then you have to think about the function, you have to define and check about the complexity, about the performance, cost, area, environments, or manufacturing details of power needs. Say, just take the example of automotive. Okay, for this automotive sector, you are having one CPU, for which we are calling that as a ECU. Okay, so that ECU that is going to be work along with your car. Okay, and what is the temperature within that car? So that is kept along with your near to the engine. Okay, so along with that near to the engine, so within the engine the temperature rises up to the 1,000 degree. Okay, but outside of that engine, that temperature rises up to 200 or something. Okay, so then your processor should be there, which should not change the logic. It should not change the logic from one or zeros, and still it should get work. So we need that ECU. You know, we should need that processor where there should not be any changes because of the temperature. So we'll see that operating temperature range that should get matters whenever you are thinking about the automotive sectors. Okay, so here they have mentioned the temperature shocks that might be there, or thermal performance for that processor. So if we are thinking about the automotive sectors, then definitely we have to think this part. Okay, then the most important feature which is available along with this CPU, that is a hardware acceleration feature. Okay, so this hardware acceleration, that is what the speeding of the CPU. So the hardware acceleration means, do you want to work along with the multimedia, or do you want to work along with the that Wi-Fi, or do you want to work along with the communication side? So how we are utilizing or how the applications are there. So in that way, you can implement the hardware acceleration feature. So what is hardware acceleration feature? So that is what the designing, or that is what the CPU manufacturing, we can say that is a CPU manufacturing, how the hardware within that CPUs get manufactured. So we are having the different technology. One is the directly we can have that CPU, the second the ASIC part, the third one is FPGA. So if we are having this smaller module, a small module of that CPU, that can be developed in terms of this uh, as FPGA, or in terms of the ASIC along with the whole that CPU, then the some of the function that can be executed very fast when we are having the ASIC, or when we are having the FPGA within your whole CPU chip. And that is what this hardware acceleration feature. And now what the arms are available, what arm that 9 or 11 families are available, they are along with this feature, they are having this feature, that is a hardware acceleration feature. And then you can think so if you need the multi processing option, so multiple tasks that should get executed, then okay, other rather than one core, you might have the multi core within your whole one CPU. And if you are having the multiple core, so multi-core, quad core means what? So there are the four CPUs are available there, and four CPUs are connected together, and they can execute it at a time. So the multiple tasks can be executed, and then you are getting the result faster. So we have to think for these features where you are selecting any CPU. Then here just example has been given for the medical. We are concerned with the safety. Okay, for the media player, we are concerned about the hardware acceleration. So hardware acceleration means the multiple tasks should get executed. Okay. Then for the wireless communication, the security we are checking up. Then the storage and the networking, we always check it out the expansion of that system. Okay. So these are the parts where we should consider when you are selecting the CPU. Now we are having the CPU as an ARM. There are the multiple versions of that ARM. Then out of that one, which one can select it, or which we should select. So depending upon what type of the requirement is there, then what type of the application is there, depending upon this requirement, depending upon the performance, then we can select one of the ARM processor. This is the one area where we should think. The second is the support. So what type of the support has been provided with this CPU. Okay. For example, here we are just taking the example EtherCAT protocol. Okay, suppose our industrial application need that EtherCAT protocol, so that the data which has been provided to this CPU, that is going to be connected along with this protocol. And if my CPU they are along with this protocol, then I doesn't require any additional add-on circuitry or add-on software routines that should be there along with my system. So at this moment, then I should check it out key such type of the support, is it there along with the CPU or not, and then I will select such type of the CPU, isn't it? Then the next part is the bandwidth requirement. So normally the bandwidth with respect to the data or memory, almost 25% additional capacity processor we are selecting. Suppose we require the means 1 megabytes of memory, then we'll try to have the 2 mega or 1.5 mega if their availability. Otherwise, then we'll go with the highest one, that is a 2 mega, and then we'll keep that one. So whatever the requirement, we are not going with that one. So we'll have some additional with the higher capacity device, so that after some times, if we have to add some routines, then only the same system should get executed. So normally we are just thinking about the at the level of that designing, just we are calculating the theoretical values, what would be the maximum bandwidth supported for the system in terms of the speed and the data rate, and then we are adding above that one. So the implementation, so validate that bandwidth with respect to the software overheads and the speed limitation. And then at the testing, so at the testing levels, we are always running the worst conditions, so that our system should get executed. So that is regarding with this bandwidth requirement. So what I so the lastly what we can say that the choosing a processor or matching a processor, the immediate application is important. Okay, so it is significant to prevent the system failures, especially for the embedded applications. Okay. So in a good processor, there are usually two processors running with the same data. Okay. So if there is any mismatch, an alert is triggered in the circuits. And the second aspect to look for the interrupt latency, which can affect the real-time schedule. Okay. So these are the two different parameters at the last will consider while choosing the processor. So can we have this multi-core system? Okay, so multi-core means the quad core, or so that there are the two or many processors that are there within this system, so that will we can see, so that we can see that whatever the processor is got selected here, so it is getting work for the for that desired output function. Okay, and then this is the most important part here. So we should have this processor to check it out. There should be minimum interrupt latency. The interrupt latency means whenever that interrupt occurred at the same moment, at the same instant, that routine should get executed. Okay, so that is what the means response time. So we should have the perfect response time. So whenever the interrupt occurred at the same moment, that interrupt routine should get executed. Then we should check it out whenever we are going for any ARM processor. For example, if you go for the ARM 7 or 9, the simple interrupt controller is available. But when you are going for the ARM 9 or 11, we are having the vector interrupt controller, and that is a part of that processor itself. So that it will have their own structure, interrupt structure, their interrupt buffers, so that the addresses are there along with that vectors. They are calculating the address and they are sending it to the CPU for the that routines, or for the expected routines. So again, there are the many interrupts are provided to that CPU out of that one, which should be occurred first, so that privilege interrupts or the uh, priority based interrupts. So these features will check it out depending upon what type of the embedded application is there, and depending upon that one, then we'll select which type of the CPU. Okay, so in a short, what I mean to say that we are having the ARM series. Okay, when we are having the ARM series, out of that one, which ARM should be get selected? Okay, now we are having the series of that ARMs, then we are having the application, and when we are having the application, then we are having the requirement. Okay, so what would be the function for that application? What type of the output functions are required? And depending upon that output function, then we'll select the ARM. For example, we require only monitoring the data. Okay, and just sending that data. We doesn't require to act on. Okay, so at that moment, then I can use only the ARM 7, where I can just go for this monitoring, and then just calculate, just monitoring the data and just saving that data. But suppose I need to act. Okay, for example, in automotive sectors. Okay, I have to act. Okay, so whenever I'm just pressing that brake, at the same moment that action should be there. Okay, so if I have to go with this real-time application, then I will check it out the interrupt structure. Okay, I will check it out the interrupt structure, where that interrupt should get executed at the same moment. So the minimum latency should be there. So for that one, then I will select the ARM in that way. Okay, so the different versions out of that one, different companies, they are having their own ARM. So I will check it out which features, and how I will check it out. So I am having the data sheet of that different processor. I will check it out what is required to me. Okay, and out of that one, I will select which should be there for my immediate project. So I think any doubts or anything from your side?
No,
Yes.
No, sir.
Okay, so any queries? Then we'll move ahead along with the arm again. Okay. So we'll try to see what exactly the how the data is flows within that arm. Okay. So there are the different registers are available. Okay, along with this arm processor. But whenever there are the different registers are there. Okay, and then the different the instruction these are get executed. So this is a very simple code. Okay, so where we can have the pipeline action. So pipeline action means the one is the fetching of the data, the second is the decoding of that data, and the third is the execution of the data, and the fourth one is the write back the data into the registers. Okay, so can have got it. The first one is the getting the data into this CPU means the fetching of the data. Okay, so for that one we are having some buffer. Then second is the decoding the data. So whatever the data is available, whatever the opcodes are available, operands are opcodes are available, that opcode get converted in terms of the signals, and depending upon that signal, then the next operation get executed. So the fetching, then the decoding, and then the execution. So here the suppose the one data is available into the one register, so that is Rn. The second may be available into the Rm. Suppose the addition is there, so that addition that may have some opcode, so that that is decoded, and that decoded signal that will ignite this ALU in a such a way that the whatever the inputs are available on this Rn and Rm that should get added, and the result should be right back into the one of the registers, that is the destination registers. Okay, so there are the two operands are there, one is the A and B. So along with that instruction, so one opcode, so that is going to be decoded, two operands. Okay, and third is in destination. So that instruction get executed here, depending upon which type of the instruction. And if we doesn't have that thumb instruction or thumb instructions, or 16-bit or 32-bit, so or you can go for the sign operation, then the sign extended operation might be there, and that is going to be sent to the registers. So there are the different registers are available here. Okay, out of that one register is used as a PC, and the program counter, which gives you the location of the next instruction, which is going to be fetched inside the CPU. Okay, so whenever the one of the data is available here, the directly it will give the signal is provided here. The PC counter is going to be incremented by one. Okay, and and then that address has been given here. The ALU, it will provide the all operation. The barrel shifter, it shifted the multiple bit, or it will rotate the multiple bit depending upon how many bits that has to be rotated. So the multiple bits can be rotated or shifted within a one clock. That is the function of this barrel shifter. Okay, so you can get that means the in binary. What is the meaning of the shifting of the one bit? Okay, the shifting of one bit is the multiplication. Okay, so you just correlate that part. Okay, if you are shifting the one bit, so how it is correlated along with the multiplication in one direction, in other direction it is a division. So how, and that's why it becomes very faster by means of these barrel shifters. So this is what the data flow models, which is there along with the ARM processor, where you can see the pipelining concept, how so fetching as well as the decoding, the execution, okay, as well as the this write back. So these operations are overlap for a different instructions, and that is what the pipelining means. What one instruction get executed at the same moment, the previous instruction is getting decoded. At the same moment, the not the previous, the next instruction. Sorry, the one whenever the one instruction is executed here, the next instruction is decoded here, and the next instruction is fetching. So one is fetching before that one is decoding, and before that one is executing. Means three instruction at three different stages, they are executing within the one clock. Okay, within the one clock, three operation for three different instruction is getting out, and that is what the beauty of the architecture. By means of this pipelining, the execution becomes much faster. Okay, So here the that has been given what type of the architecture, that is a Newman architecture, where the data is either instruction or the data from the same memory is taken. That's why it is a Newman architecture. If that are the different, then it is a Howard architectures, isn't it? Then sign extension that convert the 8-bit or 16-bit data into the 32-bit, so that all the operations are 32-bit. Then we are having the source operands Rn and the Rm. It is going to be take back into the register with the RD destinations. Okay. Always the PC, it will define the address location of the next. Okay. So there are the arithmetic and logical unit and the multiply